Hello everyone. In last lecture I was discussing about linear elastic fracture mechanics. In today's lecture also I will discuss about the remaining parts of linear elastic fracture mechanics. Here mainly I discuss about Paris-Erdogan's law and I will solve some problem based on this Paris law, and I will also show you at the end of this lecture how to predict the critical stress intensity factor KIC, and that related things also I will discuss in this lecture. So, this is the content of today's lecture. First of all, I will discuss about the linear elastic fracture mechanics introductory parts which has remained part of this previous lecture. Then I will discuss about Paris-Erdogan's law in details. I will show you how to derive this Paris-Erdogan's law and how to predict the what it is called final fatigue life using fracture mechanics approach. That related things in details I will discuss. I will solve on problem on Paris law, and I will show you what are the effect of stress ratio on crack propagation, then what are the effect of stresses and crack length on crack propagation. That related thing in details I will discuss, and at the end I will discuss about how to measure KIC, that is critical stress intensity factor, also called fracture toughness. All of we are very well familiar that fatigue is the initiation and subsequently you can say the propagation of crack inside the material. So, in case of log-log curve, the correlationship between crack growth rate with respect to number of cycle, that is dA by dN you can say this is in log scale, you can say log, and the abscissa represent the log delta k. Delta k is the range of you can say stress intensity factor. So, this can be represented in following curve you can see. So, I have already discussed in previous lecture generally the crack propagation starts from a threshold value of you can say stress intensity factor range that I have already discussed in previous lecture, that is delta KTH, and it in first stage you can see which is the region on the crack growth which is generally slow crack growth is taken place, you can say from threshold range of stress intensity factor to certain limit, you can see where you can say the crack growth is slow. So, that is why this region is called a phase on, or you can say stage on region, you can see here, which I have represented in Roman I, you can see. Then in stage 2, which is the region, in this region the crack is stable, you can say. So, after this crack region 1 in log-log plot, once you will see it will become a stable types of crack growth. Here you can see it follow a linear types of relationship in log dA by dN versus log delta k plot, that you can see. This is called you can say stage 2, or it is called stable region. In this region 2 so called Paris law is valid. That means this Paris law in this region we can represent by dA by dN is equal to you can say C into delta k to the power m. This I will discuss in detail in subsequent slides about C, m and everything. So, in this equation this m and c are the material constant. This material constant C and m can be you can say determined experimentally, which I have written here itself. In this region this Paris law is valid and this is a linear relationship. How it is coming in subsequent slide I will show. So, after that the stage 3 generally come, that stage 3 in this region you can see, which I have represented like this. Here generally the crack propagation become unstable and it become very fast. After that a critical crack length it reaches. At this critical crack length, whatever the stress intensity factor we got, that is called KCR, that is called critical stress intensity factor. KCR is called critical stress intensity factor, which you can represent as KIC. At this KIC, when the crack become unstable, and finally at this critical stress intensity factor, you can say its catastrophic failure of the structure is taken place. So, this KIC you can represent as Y del sigma square root of, you can say, pi into AC, where AC is called critical crack length, and this KIC also have a name. This is called fracture toughness. This you should keep it in mind. This is also called fracture toughness. This you should keep it in mind. That means at a critical crack length, whatever the critical stress intensity factor value you got, that is generally called fracture toughness. This you should keep it in mind. Now, so we will discuss about more details about Paris law. So, Paris-Erdogan's law, which was you can say established, or you can say invented in 1963, and nowadays also it is very popular fatigue life estimation techniques, which is based on fracture mechanics approach. So, this Paris law generally permits one to determine the you can say propagation rate, that means crack propagation rate with respect to number of cycle for a crack length A after its detection. That means it can determine the propagation rate of a crack length A after its detection. Once the crack length A we detect, after that how it is propagating with a number of cycle, this we can determine with the help of what it is called Paris law. This law generally can be represented in damage growth. This law of damage growth is given by dA by dN, which I have already told you. This is also called, you can say, crack propagation rate with respect to number of cycle. N is called number of cycle, C and you can say M are material constant. So, where generally C is called material constant and M is sometimes called also environment parameter also. It is sometimes called environment parameters also. Generally, this C value varying from 0 to 1, that means 0 to 1, whereas this M value varying from, you can see 2 to 4 for non-corrosive environment. This you should keep it in mind. If it is corrosive environment, at that case this M value can be higher level, what I am telling, understand. But it is generally varying from 2 to 4 for non-corrosive environment. If it is corrosive environment, this value also further increase, or you can say this value can be little bit higher side also, what I am telling, understand. This you should keep it in mind. Okay. So, where A is generally called crack length, N is called number of cycle, and delta K is called range of stress intensity factor. Now, this equation how we can derive that related things I will discuss. Here you can see, if I will take this, let this is equation number 1, both side if I will take log, then what we will get, dA by dN is equal to, we can write as log C delta K to the power M. This we can write. So, where this right side we can say log C plus log delta K to the power M. This further we can represent as log C plus log M into log delta K. This we can write, correct. So, this equation in log-log plot, it follows, I have already told you, it follows, you can say, let us consider this is log dA by dN, and let this is our log delta k. So, it follow a, you can say, linear relationship. So, in xy plot what we know, that means a linear equation can be represented, let this is our x axis and this is our y axis. If there is a linear equation, then let this crossing point at y axis, whatever the things we got, that is generally called c, and the slope of this linear equation is called m, then it will be represented as y is equal to mx plus c. So, this c is called y intercept, you can say y intercept. So, here also the similar equation, if here we are representing y in terms of log dA by dN, and here x we are representing in terms of log delta k, for that case it is also a linear relationship, this equation number 2 you can see. So, dA by dN, if we compare this equation number 2 with y is equal to mx plus c, so same types of linear relationship also we got, and here this intercept, this is represent, you can say, log c, and here the slope of this equation you can write as, this is our 1 and this is our m. So, m is the slope of this equation. In case of how to find out m, you know these things very well. If there is 2 crossing point, then we can write as m equal to y2 minus y1 divided by x2 minus x1. This way also we can find out, you know these things very well. So, I am not going in details about all these things. Okay. So, here also you got these similar types of equation in log-log plot. This is also a linear relationship, and this relationship in log-log plot validates in the middle region or stage 2 region of this crack propagation rate with respect to number of cycle versus stress intensity factor range log delta k. With this generally how it is varying at middle region, that I am just showing here. But here generally this Paris law is valid, and in log-log form this Paris law can be represented as this log dA by dN equal to log c plus m into log delta k. Now, I will show in details about its derivation, how to find out the number of cycle in terms of what is called initial crack length and final crack length. So, for this actually I will show you how this derivation part is coming. So, we have already got this linear equation in region 2, which I have already shown in previous slide itself. Now, this equation, so what we got, this equation just I am just showing the derivation part, here I have shown. So, dA by dN we are getting as c into delta k to the power m, correct. So, we are interested to find out number of cycle value. So, how to find out this number of cycle value, that I am going to. So, dN we can represent as dA divided by c into delta k to the power m, correct. Let us consider the initial crack length. A0 is the initial crack length which I have written here, and AC is the final crack length, you can say, or critical crack length where the fracture is taken place. So, AC is called critical crack length, A0 is initial and AC is critical crack length. Okay. So, at critical crack length, what is the number of cycle? Let us consider at A0 the number of cycle is starting at 0, and AC where the you can say fracture is taken place, let the number of cycle is NF. So, for this what we need to do? We need to do the integration. So, we are doing integration where the number of cycle varying from let us 0 to NF dN, which will give us, you can say, directly number of cycle. Okay. This number of cycle with respect to what? You can say A0 with respect to initial crack length we are finding out. So, we can write like this, NF integration of A0 to AF. Okay. So, dA by you can say C into delta k to the power m. Now, we already very well familiar about delta k. So, delta k is equal to you can say k max minus k min, correct. This is very well known. So, what is k max? K max is generally you can say y into sigma max square root of pi a, and this y into sigma min square root of pi a, this way you can write. So, here delta k how it is coming, that I am showing. So, you can say y into del sigma square root of you can say square root of phi a, where del sigma is called stress range. Okay. This is called the stress range or range of stress, that also you can say. So, this I am writing here in this equation. So, what we will get? So, here NF number of fatigue cycle, NF means number of fatigue cycle is equal to we can write as A0 to AF dA divided by C into, instead of delta k I am writing y del sigma square root of pi a whole to the power m. So, this equation, what is the value of this integration of this equation, that we need to find out. So, this equation we can write as, if we consider here you can say sigma max, sigma min, this is the range which is for a fluctuating loading, this is constant. So, del sigma also we can say is a constant value, and C is a material constant. So, for a particular material this is also constant. So, these are the things we can bring out from the integration part. So, 1 by C, once we bring all this thing out, that is C, and phi root over pi is there. So, it will be m by 2. Okay. So, and del sigma to the power m will be there, correct, and integration of A0 to AF you can write as dA divided by y to the power m and a to the power m divided by 2. These are the equation we are getting. This equation I am writing, this is equation number 2. So, this equation actually we need to solve. Now, if we consider let us this material constant y, or you can say geometric constant y is constant, then what will happen? And if we consider y is not constant, if y is also a function of what is called crack length a, then how it is, how will be the solution, that related things I am going to now show. This equation solution now I am going to show. So, if we consider, just here I am showing, if we consider y is constant, that means constant in the sense which is not a function of crack length, that means constant means which is not varying with crack length, a, then what we will get one types of solution. If it is not constant, then we will get another types of solution, that I am going to show now. So, you see, so for here first of all I will show you, if it is a constant, that means if it is not varying with crack length, then what will be the solution, that related things now I am going to show. Okay. In previous slide itself I have shown what we got, NF equal to we got as 1 by you can say C pi to the power m by 2 del sigma to the power m integration of a0 to af dA divided by ym a to the power m by 2, correct. This equation we got. So, two cases. So, this is equation number 2 I have already told. So, for case 1, two cases I will discuss. So, for case 1, if y is constant, y is not a function of crack length A, then what should be its solution? That means y is constant, you can say y is constant. Then what we can say? We can bring this y also out from this integration part. So, from equation number 2 what we can get? So, using equation number 2 what we can get? What should be the solution? NF we can write as 1 by C pi to the power m by 2 del sigma to the power m, okay. And here ym also we will bring out, okay, from the integration. So, we can write as this will be a0 to the power af dA divided by, you can say, a to the power m by 2. So, here this left side part, let us consider, we consider a value, let us consider this is capital A, okay. This capital A integration of a0 to this what is called dA by a to the power m by 2, we can write as a to the power minus m by 2 plus 1. So, this I am writing here, that will be better. So, this integration part we can write a into integration of a0 to af a to the power minus m by 2 dA, okay. This we can write as a to the power minus m by 2 plus 1 divided by minus m by 2 plus 1, correct. This we can write, where the limit is varying from a0 to af. So, this we can further write a, and m is also a constant. So, we can write af to the power minus m by 2 plus 1 minus a0 to the power minus m by 2 plus 1. This way we can write, correct, divided by this 2 is, so you can say minus m plus 1. So, this we can further write 2a divided by 1 minus m, okay, 2a divided by 2 minus m, this should be 2, this should be 2 because minus m plus 2 by 2. So, this should be 2 minus m, and here it is coming as af, you can write as 2 minus m divided by 2 minus a0 into 2 minus m divided by 2. This you should keep it in mind. This is the solution for case 1 where y is equal to constant. This is one way we can get the solution of Paris law. Now, if this y is a function of crack length, then what should be its solution? Now we will discuss about case 2 where y is varying with crack length, then what will be the solution, that I am going to show. Okay. So, for solving these things I am going to show if let us consider y is a function of what it is called crack length A. So, now we will discuss about case 2, case 2 where y is a function of you can say crack length A. Then what should be the solution, that I am going to show. Okay. Let us, we are considering y a is equal to its initial value y a 0. So, here I have, so here we are assuming y a is a function of its initial value y a 0. So, for this case, if it is y a 0, then in this case let us consider y a, which is generally depends on initial value y a 0. That is why we consider delta k. Here delta k is not constant, we consider delta k is also what it is called, you can say delta k 0, you can say a square root of a divided by a 0. Then what happens, what will be the solution, that we are going to discuss. Okay. For discussing these things, how the solution is coming, that I am going to show. So, if delta k is a function of delta k 0 and it is a function of crack length A by initial crack length A 0, then what should be its solution, and where delta k 0 you can write as y into A 0 till sigma square root of pi A 0. This you should keep it in mind. Then what should be the solution, that I am going to show. So, how the solution is coming, you see. So, here we consider instead of delta k, here we are considering delta k is equal to a function of y a 0 and also a function, also a ratio of a square root of a by a 0. Then what should be the solution, that I am going to show. So, for solving these things, what we consider, y is a function of a 0. A 0 means initial crack length. So, we can write as delta k is equal to delta k 0 square root of what it is called a by a 0. So, if it is like this, and where what we consider delta k 0 equal to, you can write as y a 0, it is a constant, okay, y a 0 and del sigma square root of phi a 0. This you should keep it in mind. Now, this we will use in equation number dA by dN, you can say equal to C delta k to the power m. So, here in delta k we are going to use y a 0 del sigma square root of a 0. This we should keep it in mind. So, that I am going to show. So, this C into what I am using, delta k 0 square root of a by a 0 to the power m. Okay. Now, from here we need to find out the solution of this equation. So, number of cycle we will find. So, here dN we can write as dA divided by C into, so integration of 0 to n f, this will be equal to, you can say del sigma 0 is a constant because it depends on initial crack length. So, that way we have written. So, delta k 0 to the power m, okay, and a square root of what? A square root of a by a 0 to the power m is there, okay, and here this is varying from a 0 to a f. So, for this case what should be the number of cycle NF for this case if y is a function of crack length YA0, then what should be its what solution, that I am going to show. So, this you can get. So, as delta k0 is a constant, so we can bring it out from the integration, and c is also a constant, so we can bring it out from the integration. So, we can bring this c into delta k0, which is a function of a0 only, you can say. Okay. And so, this I can bring it out. So, in integration a0 to af, you can write you can say a square root of, so here I am writing a square root of a by a0 to the power minus m dA, correct. This we can write. So, this we can further simplify, like you can say 1 by c delta k0 to the power m, delta k to the power m. This we can write as, you can say a square root of a by a0 minus m, or you can say minus m by 2 plus 1, okay. This divided by minus m by 2 plus 1, and the limit is varying from a0 to af. So, this we can further write as c into delta k0 to the power m, and here this, if I will just do the calculation, what we will get, 2 divided by 2 minus m, and here will be for a0 this will be 1, this will be 1, and for af this will be minus af by a0, you can write as to the power, you can say 2 minus m divided by 2, this way you can write. So, this is the solution for what, if y is a function of y0, this I have already written. So, y is a function of, you can say ya0, then that means for this case how the solution is coming, that I am showing. And here use delta k is a function of, you can say what it is called crack length A. So, delta k is considered here. So, you can say here delta k we are considering a function of crack length. So, here in this case what we consider, delta k is a function of, you can say crack length A, this equation, it depends on delta k0 value. What I am telling, understand how it is coming, I have already shown. So, for this case our solution is coming like this. So, here always you should keep it in mind, here m should be greater than, you can say 2. So, for m greater than 2 this equation is valid. If m equal to 2, then what will happen, that also you need to know. So, that I am going to show. So, for you can see for NF, for m not equal to 2, for this case we got the solution is this. This I have already shown in the shown the derivative parts. Now, if m equal to 2, then what should be the solution? For that case our solution will be like this. How it is coming, that also we should know. So, for m equal to 2, we use in this equation number, this is the equation number 2, in this equation number 2 if we will put the m equal to 2, what we will get. So, you can see, so here NF should be equal to integration of, you can say a0 to af. So, here generally dA divided by C into, and delta k I have already shown as what it is called, delta k 0 square root of A by A f, correct. So, here we consider this to the power m equal to, if it is 2, then what will happen, that I am going to show. So, if it is 2, then we can get as directly we can say, so 1 by C delta k 0 square, okay, integration of A 0 to A f. This you can use in equation number 2, or you can say equation number 1 itself. This, by using this equation itself we can get this relationship. So, dA divided by, you can say, A by A f, correct, this we can write.